Okay, so ladies and gentlemen, good afternoon. Welcome to the Triple Science Part 2 Physics Hangout. So it's now 4 o'clock, so I'm going to make a start. Don't forget that you can post comments onto the frog page. Just let me know that there's someone there as I'm giving this broadcast, but of course I know most of you are going to be able to watch this back. So make sure you've got pen, paper, calculator, and I'm going to try and give you some kind of top tips on the second half of this physics, go through some practice exam questions, and hopefully make you feel nice and prepared for the P3 exam in a couple of weeks or 3 weeks. Okay, so let's get started then. If we have a look at the topics that appear in this P3, the second half of P3, we're going to be taking a quick look at moments. We're going to be looking at centre of mass, how to find the centre of mass, and looking at stability. We'll be looking at some hydraulics, some circular motion. Then we're going to look a little bit at magnetic fields, motor effects, and transformers. Okay, so if you're ready, if you watch the first half of P3, you'll notice that my handwriting isn't very good in these. It's just to make you feel kind of reassured that handwriting doesn't have any effect on your mark in physics. Okay, so looking at this at the first topic then, so moments. So a moment is a turning force, so it's just like a force, but it acts in turning things rather than pulling or pushing. So the equation for a moment is moment equals force times distance from the pivot, and that is a perpendicular distance. So here we have our nut, which can be described as the pivot, and if a hand was operating this spanner to be able to turn the nut, to be able to apply a moment to it, a turning force, well then we would simply do your force multiplied by your distance, but take care that the units for distance is in meters. So my 15 centimeters would become 0.15 meters. Okay, so I'd simply times my 100 newtons by my 0.15. Okay, so 100 times by 0.15. Okay, so here's our equation of moment equals force times distance from the pivot, and the unit for moments is Newton meters. Now you can always work that out in the exam because, of course, force, the unit for force is newtons, distance, the unit for distance is meters, and since they're multiplied by each other, they're just next to each other. So Newton meters is the unit for that. Okay, now the science behind this equation tells us that if we wish to apply a bigger turning force, well then the easiest way to do that is to apply the force at a bigger distance. So if you were to hold the spanner further down towards the end of the spanner, you're going to be able to apply a bigger turning force to the nut there. So so for a stronger lever, you can either apply a larger turning force or a longer lever. So levers are known as force multipliers because you can apply one force at one end of the lever and it can apply a much bigger turning force acting on the load there. So we can think of them as force multipliers. So for example, if we look down here at scissors, scissors have got our pivot here. We apply an effort quite close to the, we apply an effort quite far away from the pivot there. And you may have noticed this when using scissors, that the closer to the pivot, the easier it is to cut through things. So if you're cutting through card, you'll be putting that nice and close to the pivot there, or the fulcrum. And similarly with hammers as well. So if you were to try and pull out a nail with your fingers, nigh on impossible. But because you're applying your force with your hand at the far end of the hammer, there's a large perpendicular distance away from the pivot, which is down here. So you're going to be able to apply a much larger turning force to the load that you're trying to apply there. Now, the other thing that we need to use moments for is that we will be expected to look at balancing objects, so balance beams, seesaws, that type of thing. Now, the science behind this is that if the seesaw is balanced, the clockwise moment must be balanced perfectly by the anti-clockwise moment. Or really all we mean by that is the kind of turning force. So here we've got Garfield, his turning effect must be the same as his buddy, Odie. I'd nearly forgotten that one. So Odie's turning moment will be balanced by Garfield's. Now we can just apply the equation to both sides. So we know that the force times by the distance of Garfield, so force times by the distance of Garfield must be equal to the distance times the force of Odie. Okay, now take care that they may ask you, what is the turning effect from one half if there was to be another person on the seesaw? Well, if you have to work out the total anti-clockwise moment there, you would take the force times the distance of Garfield and then add it to the force times the distance from the second person. Okay, and you simply work out the moments for each separately and then add them together. Okay, so let's have a little look at an exam question then that will ask us about moments. So if I was going to go through this in the exam, I'd have my highlighter in my hand to start off with. And the diagram shows a design for a crane. The crane is controlled by a computer. Okay, so what does it tell me in the question here? Well, I've got this distance here. There's the axis of rotation, or the pivot just there. Here's another distance. Here's my load. So 60,000 newtons is the weight of this object being picked up. That's 6.4 meters away from the pivot. And on this side, we've got 2.4 meters on this side. And this here is a pulling force coming from this gears and motors box down here. So carrying on reading the question, we've got the purpose of the motors and the gears is to change the pulling force in the steel cable. This is done so that the jib, and this here is the jib, is labelled up there, so the jib stays horizontal whatever the size of the load or the position of the load. In other words, the moments are balanced. So that's going to have to be something that I'm going to need to use in order to get full marks for this question. Now it gives me the equation here that moment equals your force times by your perpendicular distance. Okay, so calculate the moment. I'm going to underline that because that's what it wants me to work out. Caused by the load in the position shown in the diagram. Show clearly how you work out your answer and give the unit. Okay, so the moment caused by the load is going to be our perpendicular distance times by the load there. So let me just clear the screen down. Okay, so our distance times by the load. So 6.4 times by 6,000. When I put that into my calculator, that gives me 38,400 Newton meters. Now there would be 3 marks for that, 1 for the correct substitution, 1 for the correct answer, and 1 for the units. So knowing your units is really, really important for you. Calculate the pulling force that is needed in the steel cable to keep the jib horizontal. So we need to calculate this pulling force here, and we know the distance, and we know that this anti-clockwise moment must balance the clockwise moment of these two systems. So then I'm going to use this same equation, but this time I'm going to rearrange it a little bit. So I know the total moment. I also know the perpendicular distance, and so I am going to try and find force. So I need to find force, so F equals, well, I divide both sides by the distance, and it will cancel out from the right hand side, and it will appear on the left. So that'll be moment divided by distance. Okay, and this time it is 38,400 divided by my distance, which is 2.4, and it helped me to be able to pick out the number because I'd circled it, easy for me to see as I go through the exam. So 38,400 divided by 2.4, put that into my calculator, and that gives me an answer of 16,000. And this is where I can just look back at the question, and I should have underlined the thing that it's asking me to find. It wants me to find the force. Well, that's easy enough because I know now that the unit on the end is going to be newtons. Okay, good. And don't forget, you can pause this video at any point and you can just go back through, pause it on the question, have a go at the questions yourself, and then watch my my workings out. Okay, so centre of mass. We need to be able to define what the centre of mass is, and we also need to be able to work out how to find the centre of mass for regular shaped objects and irregular shaped objects. So, I mean, what is centre of mass then? Well, centre of mass is the point at which mass is evenly distributed. So what I mean by that is, if I get any shape, the centre of mass is going to be the point where there is an even amount of mass above, below, to the left, to the right. Okay, so for a circle, it's quite obvious it's going to be right in the middle. But if we look at some other regular shaped objects, to find the centre of mass, you just use the lines of symmetry in the object. So you go from corner to corner, the point about which you can fold it in half or reverse it. So look for the lines of symmetry in the object, and where the lines of symmetry cross, that's going to be our centre of mass there, and there. So for a regular shaped object, quite easy. You can do that just by using a ruler and going from vertices. Okay, so then what about for irregular shaped objects? So here we've got, in this example, it's a lamina, which is just a thin sheet of plastic or material. And to find the centre of gravity or centre of mass of an irregular shaped object, what we want to do is we want to hang the object from a suspension point. So we can see here's our irregular shaped object, and they're hanging it from a pin, and around that pin they're also hanging a piece of string. So they're letting the object hang freely, and as it hangs freely, gravity is just going to be pulling it down. Gravity is going to pull it down in such a way that the centre of mass is always going to hang directly below the suspension point. So hang the object from a suspension point with a mass on a string, freely hanging, so that gravity is pulling it straight down to the centre of the Earth. You mark the line on with some little crosses here. Then we hang the object from a different suspension point, and then we repeat the process. So here we can see the previous center line. We're going to hang it again from a new suspension point. Again, the center of mass is going to be directly below the suspension point, and then 1/3 time, and we should find that on our third time of hanging it freely, that our line, our vertical line down, crosses through the same point as the other two. So our center of mass is where the lines cross. Okay, so for a lot of talking, how can we kind of boil that down into a really simple way of explaining what this is? Well, we hang the object from a suspension point with a mass on a string, freely hanging. We mark the line on it, hang from another point, and repeat it. Drop mark on the line, and the center of mass is where the lines cross. Okay, now we need to be able to work out what objects are stable. Stability is important with things like Formula One cars, or buses, as we see here. So what science is there behind things being stable, and how does the center of mass affect this stability? So if I just go back to this slide, so low and wide objects are the most stable. Here we've got two vehicles. One is tall and thin. One is wide and low. And we can see here that they're both tipped up to the same angle. But when they're both tipped up to the same angle, we can see here that the center of mass has moved outside of the base. So the base of the vehicle is on its wheels. When I tip it up to this angle here, we can see that the center of mass lies outside of the base. So this car here is going to topple. Now, when this black car is tipped up to the same angle, we can see that the center of mass line still lies within this base here. So this vehicle is not toppling. Okay, so as we can see here, this vehicle is not toppling. Now, double-decker buses are famous for being able to be tipped to a very large angle, and the main reason for that is because their center of mass, the center of mass is so low inside the vehicle. You can imagine that if the center of mass was right up at the top, it would tip over. It would tip over at a much lower angle, but because the center of mass is very low, that the bus will be harder to tip, because the center of mass, or the line of action of the center of mass, that's really what we should say, that the line of action of this lies within the base. So there's no resultant moment. A resultant moment, just like a resultant force, would be an overall kind of tipping force. So again, with this one, we can see that at a much higher angle, finally, the line of action of the center of mass is now outside of the base. So this bus will topple. There's a resultant moment, so it's going to fall over. Okay, so that's how to find your center of masses for regular shaped objects, irregular shaped objects, and how the center of mass affects the stability. Okay, so if we have a quick look at this exam question, lovely 5-mark question here, and fingers crossed that this comes up because this is nice and simple. So figure 1 shows a sheet of card. Describe how to find the centre of mass of this sheet of card, and you may draw diagrams as part of your answer. Okay, so at this point, if you want to have a go at this question, feel free to pause the feed, and we can you can pause it, have a go at the question, and then just replay it yourself. Okay, so if we were to look at how we would answer this, well, we need to kind of give some bullet points and a short, concise way of how to explain this. So the first thing to do is to pick a point on the object and hang it from that, suspend the shape from a point. So we can put a pin in that shape there and hang it from there. And you can show, you know, from the mark scheme, we can show, you can show in the answer where you're going to suspend it from. Then you're going to, for the second mark, you're going to attach a mass on a string. So the first, if I write them out in shorthand, suspend shape. Okay, that just means hang it. Secondly, you're going to attach, now we call these a plumb line because plumbers used to use them, but attach a mass on a string. So that's going to be 1 mark each. Now then, the next thing we're going to have to do is we're going to have to mark where the cross appears on the object. So mark line, either with crosses or just a straight line there. So that's going to be your third mark. Fourth mark is suspend from another point. So this time you might want to hang it from over here. And mark line again. Okay, and you should find that when you hang it that way, you'll have another line like so. Okay, and the last mark is going to be for saying that where the lines cross is the centre of mass. So I'll just shorten that to C-O-M. Okay, so suspend the shape, attach a mass on a string, mark the line, suspend it from another point, mark the line again, where the lines cross is the centre of mass. Okay, so nice and straightforward. Let's hope that one comes up in the exam. Okay, so other questions. So the questions will either be about finding the centre of mass or looking at a question like this about how centre of mass affects stability. So if we have a look at this exam question, here we've got person 2 shows a person in his wheelchair. Tipping the wheelchair at a large angle may cause it to become unstable and to topple over. So explain why. Now this is for 2 marks. So again, you can pause it at this point and have a go at this question on your own. Otherwise, for the answer, we'd be looking for that the line of action, so if we imagine the centre of mass is, well, probably quite low down, just here, and we look at the centre of mass. If the centre of mass, the line of action of the centre of mass is inside the base, it won't topple over. So to explain why tipping it at a large angle will cause it to become unstable, well, we want that the line of action of weight or centre of mass, I'll just shorten that to COM, that the line of action of the weight or the centre of mass lies outside the base. Now that is all for 1 mark. The second mark is going to be to say that there is causing a resultant moment for the second mark. So if the line of action of the weight or the centre of mass lies outside the base, there'll be a resultant moment to explain why he's going to tip over. Okay, so for the next 2 marks, for the next question, some disabled athletes use a wheelchair in sports. State 2 ways of changing the design of this normal wheelchair into one which would be used for sports. Okay, so to make it more stable, well, we know that how high up the center of mass affects the stability, and also the size of the base. So we could pop in here that move wheels apart. That would increase the size of the base, or to lower the seat. That would lower the center of mass. Okay. Okay, so a very short little bit on pendulums. There's not a great deal that we need to know about pendulums, and most of it lies in this equation here, but a little bit of the science behind pendulums. So pendulum describes anything that's going to swing backwards and forwards, and the longer the piece of string, the longer the time period for one oscillation. And that kind of makes sense. If you've got a really small piece of string, it's going to swing backwards and forwards quickly. Really long piece of string, it's going to take a long time to swing backwards and forwards. Now, it's important to know that one oscillation is there and back. So from the start point over to the end point and back again equals one oscillation. Okay, that it's not just from one side to the other, but there and back again, so a complete cycle. Now, the time for one swing is found by 1 over the frequency. I mean, frequency tells us how many times a second something will swing. Well, to work out the time for one swing, it's just 1 over the frequency. Okay, now don't forget that there's a possible circular motion link to this. So we're going to look at circular motion shortly, but it is possible that they might ask us some circular motion questions about pendulums. Now don't forget that the tension in the string would cause the circular motion. There will always be a centripetal force acting towards the pivot up here. That would be the centripetal force. Don't forget as well that they could talk about maybe a theme park ride where the effect of increasing the speed of the oscillation, how that affects the centripetal force. Of course, increasing the speed will increase the force. If I reduce the radius, that will increase the force. But we'll look at that a bit more when we look at the circular motion questions. So just to make sure that we're happy with our pendulum and the equation here, so highlighter out, a large clock keeps time using the swing of a pendulum. The frequency is 0.5 hertz. Calculate the periodic time of the pendulum using my correct equation. Well, that's going to be T equals 1 divided by F, which equals 1 divided by 0.5. Put it into your calculator. Easy to make slip-ups with simple sums like that. That's going to give you an answer of 2 seconds. Okay, calculate the number of complete swings the pendulum would make in 60 seconds. You've got to use your answer from B1. Now, if you for some reason ever struggle to come up with an answer and you see that answer then gets used in a second question, make something up here. Because if you make a mistake here and you use that same wrong answer here, you can get full marks. You still get full marks if you use an incorrect answer carried forward. So be prepared to just carry forward a wrong answer. Still do the right calculation and get the right answer. So in 60 seconds, if each swing takes 2 seconds, divide my 60 divided by 2 equals 30 swings. Okay, lovely. Okay, so hydraulics then. Now, hydraulics are devices, they're force multipliers again, so that allows me to put in a small force at one end of my, my hydraulic system, and it will apply a much larger force. So this here is a car jack, and of course I would never be able to apply enough force to be able to lift up a car with one hand, but by me applying a small force, but moving the handle a long way, I can apply a much bigger force, but just over a smaller distance. You're probably familiar with seeing these in hydraulic systems on JCBs and diggers. We see them. These are these kind of tubes within a tube. So what do we need to know about hydraulics? Well, let's have a look at a hydraulic system, and we're just going to make sure that we can label all the parts on it. So this would be the inside of a hydraulic system, and you'll see that on one side of the hydraulics. This will be where I'm pushing. I'll be pushing on the smaller side. This is called the master piston. And this one over here, this one does my bidding. So this is going to be called the slave piston. Okay, so I'm going to apply a force to the master piston, and a force is going to be applied by the slave piston. Now, there is the reason why pistons work or hydraulics work is because of a kind of bit of science about the liquid that's inside it. Now, it works because liquids are incompressible, which simply tells me that I can squeeze water and it will transmit my force or my pressure, transmit my pressure equally in all directions. So because liquids are incompressible, when I squeeze over at this end, that pressure that I apply here will also apply over here, because the water has to go somewhere through this device up here. It has to go somewhere. So liquids are incompressible, and my pressure is transmitted equally in all directions. Okay, that's why hydraulic systems work, because the liquids are incompressible. Whatever pressure I apply on one end, it'll apply that same pressure up to the other end. So when we look at doing calculations with this, if I know, let's say what force I apply, and I know the area of my my master piston here, I can calculate my pressure. So if I know my force that I'm applying and I know my area, well, pressure equals force over area. And I said that the pressure is transmitted equally. So my pressure here will be the same as my pressure here. But of course, what's different? Well, my area here is much bigger. Now, if my area here is bigger, in order to keep the pressure the same, my force also has to become bigger for this statement to be true, to still be true. So I apply a force over a small area, and a bigger force will be applied over a bigger area, all because my pressure is constant inside a hydraulic system. Okay, so here we can see that the force divided by, we can see that the force divided by the area at the master piston is the same as the force divided by the area at the slave piston. So we use this to be able to solve problems. So if we have a read of this exam question here, figure 1 shows parts of the lifting machine used to lift the platform up and down. Let's get the highlighter out and highlight some information that it's giving us here. So we know the cross-sectional area of the piston. We've got our celebrity there, and this platform is going to go up and down. Here's our pump, which is applying a pressure to the water. So what type of system uses a liquid to transmit a force? Well, it's a hydraulic system. And the pump creates a pressure in the liquid of 8.75 times 10 to the 4 pascals to move the platform upwards. Calculate the force that the liquid applies to the piston. Use the correct equation from the physics equation sheet. So I want to calculate the force, and it's telling me the pressure and it's telling me the area. So my equation of pressure equals force over area. If I just rearrange that to make force equals pressure times area, just multiplying both sides by A. So the A moves up here, and on this side, the A divided by A turns into 1. So force equals P times A. Now we can keep the numbers into standard form, in which it would be 8.75 times 10 to the 4 multiplied by 1.76 times 10 to the minus 2. Now, if your calculator, for whatever reason, doesn't like using standard form, or you don't like using standard form, feel free to rearrange it. So you'll know that to the positive power means you move the decimal point 4 times, so 1, 2, 3, 4 to the right, and here when you got to the negative power you move the decimal point to the left twice. Okay, so this number is going to become 0, 0 times by 0.0176. Okay, now when I put these two numbers into my calculator to calculate the force, that comes out as a lovely 1540, and they give me my unit already, so 15400. Okay. So one other extension to that question. So here we have again the pressure applied to the hydraulic system at the master piston is the same as the pressure applied by the hydraulic liquid to the slave piston. Here again we've got our force, here's our area. On this side we've got our area and we don't know the force. Well, because pressure is transmitted equally in all directions here, I know that I can work out my pressure on that side, and if the pressure here is going to be the same as the pressure here, so I can eventually work out my force, which is missing. So state the property of the liquid that keeps the pressure at both pistons the same. It's because it's incompressible. And a 360 Newton force acts on the master piston. Use the information to calculate the force applied by the hydraulic liquid to the slave piston. So it wants me to find this force up here. Okay, so use the equation from the sheet. Well, I need to calculate the pressure on the left-hand side, and you can get you'll get a mark for that on its own. It's a three mark question here. So the first mark is given for working out the pressure on the left-hand side. So P equals F over A, and that's going to be 360 over 0.0012, which comes out as 300,000 pascals. So one mark just for that, but we're not finished yet. We've just worked out that the pressure on the left is 300,000 pascals. Well, that same pressure is going to be applied in this because water is incompressible. It doesn't get squished, so it transmits the pressure. So on this right-hand side, now we need to have a new equation for this right-hand side. So I want to work out F. So if P equals F over A, then F equals P times A. So my pressure is 300,000 times by my area, which is 0.28 meters squared, and that should come out as an answer of 84,000, and that is a force. Thankfully I underlined it there to be able to see it clearly. 84,000 newtons. Okay, lovely. Okay, so circular motion then. So circular motion, objects that are traveling in a circle, and in order to be able to explain these, we need to just look quickly at velocity. Now, velocity is like speed, but includes a direction. Now, as this ball travels around the center of its orbit there, the ball can be seen to be changing direction. At any one moment, it's traveling perpendicular to the radius there, but we can see that it's changing direction all the time. Now, if velocity is speed and direction, then our velocity is changing. Even though the speed of the object may be the same, the velocity is changing because velocity includes direction. So if the velocity is changing, well, acceleration is the measure of the change in velocity. So if the velocity is changing, it's also accelerating, because acceleration is the rate of change of velocity. So we can say that this object's velocity is changing and it is therefore accelerating. And the direction of the acceleration is towards the center of the circle, okay, to keep it in a circle. If at any point you were to, if this ball was on a string and you were to snip the string, at any one moment the ball would keep going in a straight line perpendicular to the string. So it must be accelerating towards the middle. That's what's keeping it in circular motion, as we can see here from this rock on a string. So the This is caused by a resultant force. This acceleration is caused by a resultant force. And we call that force centripetal force. So centripetal force is the acts towards the center of the circle there. Now, examples of there's really three examples of circular motion and centripetal force that you need. So a car going around a road will have friction, which is responsible for the centripetal force. Of course, really it makes a lot of sense, because if there was no friction between the wheels and the car would slide off the road in a straight line. So it's friction between the tires and the road which is keeping the car going round the corner. The next one is gravity. So for this one it's friction. This one here is our example of the moon going around the Earth, or in fact any satellite going around the Earth. The centripetal force responsible for keeping it in its orbit is gravity. And then one last example that you need to know about is objects which in circular motion which are being held there by either a string or a structure. So here we've got a kind of funfair ride with seats on the end of string. So that there is being held in place by the tension in the string. So there is tension acting towards the center of the circle there. Okay, now if we wanted to increase the centripetal force, as in if we look at this boy spinning the rock on a piece of string, if we want to increase the force that is being applied there, well, there's a few things we can do to change this force acting towards the center. We could make the rock go faster. So we could increase speed. If you've ever spun a conker around your head, you'll be able to feel in your arm that the faster you spin it, the harder you're pulling against it. So increasing the speed. We could increase the mass. You can well imagine that if I was to spin a bowling ball on a piece of string above my head, that would take a lot of force from my arm. So increasing the mass increases the centripetal force. And finally, is slightly counterintuitive, this one, is if I reduce the radius. Now, if I shorten the radius, the object has to do more turning. Okay, if it's having to do more turning because it's in a smaller circle, it's having to turn sharper every millisecond, well then that takes a bigger force to make it turn more. So reducing the radius increases the centripetal force, increasing the mass, increasing the speed. Okay, so let's have a look at applying some of those theories to some exam questions. So the London Eye is the largest observation wheel in the world. There's our centre of the circle. Here are our seats around the outside. Passengers riding capsules. Each capsule moves in a circular path and accelerates. So explain how the wheel can move at a steady speed and accelerate at the same time. They love asking this question because it sounds counterintuitive, and you need to have a good understanding and explanation of circular motion in order to be able to explain this answer. Well, you could simply write down the science that I've given you. So velocity includes, oh, I've decided to change colour, that's posh. Velocity includes direction. And that acceleration is a measure of the rate of change of velocity. I've written it in quite a complicated way. It doesn't have to be written as complicated as that. So velocity includes direction, and acceleration is a measure of the change in velocity. Well, in a nutshell, it's because each pod is changing direction. And that velocity includes a change of direction, and acceleration is a measure of the change in velocity. Okay, so in which direction does each capsule accelerate? always towards the center. Okay, one more example. So what is the name of the resultant force that causes the capsules to accelerate? Well, that's going to be the centripetal force. Centripetal force. And if they'd have asked you what is the cause of the centripetal force, that would be the tension in the strings there. Okay, so the designers of the London Eye had to consider 3 factors which affect the resultant force described in Part C. 2 factors that increase the resultant force are an increase in the speed, an increase in the mass, and one other factor that has an effect on the resultant force would be the larger the radius, the less the force. Okay, and I'd be inclined to include the way that it affects it, because you can see here that 2 factors that increase the resultant force are. So I've included that the larger the radius, the less the force, or the smaller the radius, the more the force. You don't want to include in there. Okay. Okay, so magnetic fields. If we have a look at how a magnetic field is created around a wire, well, all wires that carry current, they create a magnetic field around them. So here we have a cable, and I suppose really the diagram should include a kind of idea that this is carrying current. So this could be connected to a battery, could be connected to a power pack of some kind. Now here we have on this piece of wire, we've got the direction of the current. So we can see that the current is pointing upwards. Now as the current moves through the conductor, it creates a magnetic field around it. Now to see the direction of the magnetic field, you use the right hand grip rule. The right hand grip rule is, as we can see in this hand here, is a way of us being able to see the direction of the field lines compared to the direction of the current. So the field lines will either be going around clockwise or anti-clockwise. While using your right hand, as if you are curling your fingers around the cable, your thumb shows the direction of the current. And your fingers, the direction that they are pointing, is the direction of the field lines. Okay, so in this physics topic, there are 2 rules using your hands, the right hand grip rule and the left hand Fleming rule that we'll be looking at in just a moment. So make sure you use the correct hand for it. Obviously, getting them mixed up will give you the opposite answer. Now, a little bit of the science behind these concentric circles here, or these field lines. The field lines of a magnetic force show the strength of the magnetic force. So you can see here that these lines are closer together. The closer together, the stronger the force. Okay, so we can see here that the strongest force is felt closest to the cable. And of course, if you think about it, that makes sense. A magnet, the further away you are from a magnet, the weaker the force that it's going to experience. Now, if we just clear my screen here and have a look at the creating an electromagnet. To create an electromagnet, we firstly coil the wire around in a loop, and that allows the field lines to kind of add up together. And we can still apply the right hand grip rule to look at the direction of all these, but they will all flow in the same direction if it's twisted the same way. Now we can also increase the current. So by increasing the current, there are more charges moving through, and the moving charges create the magnetic field. So the more moving charges, the bigger the magnetic field. I can also add a soft iron core. So that will be just a kind of cylinder of iron in the middle. and that will just help to boost the magnetic field. Okay, applications of these are really anywhere where a magnet can be turned on and off. So this is in a scrapyard, being able to pick up scrap metal, iron, cobalt, or nickel, and also in modern electromagnetic trains used to to accelerate the train and decelerate the train. Okay, so the motor effect then. So the motor effect is simply our last bit of science, that there is a magnetic field around a wire being brought close to a magnet. Now, if you bring magnetic field lines from a wire close to magnetic field lines from a magnet, they're going to interact with each other. They're going to either apply a force. So these two pictures show us examples of a current carrying wire being placed near a magnetic field. So the science behind how this works is if we get the definition really clear. So a wire carrying current in a magnetic field experiences a force. That is the definition of the motor effect, that a wire which has got current going through it in a magnetic field experiences a force. Now, when they first discovered this effect, this was absolutely revolutionary. I could make something, or scientists could make something move by sending electricity through it and placing it near a magnet. Now, the potentials for this were absolutely revolutionary. Of course, these days we know that we are able to have motors and generators as a result of that. So electric motors or electric generators. So the possibility of turning electricity into motion, and the opportunity to turn motion into electricity. So the national grid and power stations would never have happened without the motor effect. So if we want to increase the force, here's our wire inside a magnet. If I want to make this force bigger, well, there's only really two components in it, a magnet and a wire carrying current. So if I want to increase the force, I simply need to increase current or a stronger magnet. Okay, if I wanted to reverse the direction of the force, so we see here that the force is going upwards. If I wanted it to now move downwards, well, my only option is to flip the battery round. So I reverse the polarity of reverse the direction of my current, or I flip the magnet around so that my south is now over here and my north is over here. So if I reverse the two components, that will reverse the force. Okay, now if I want to find, if I am told, let's flip to a new screen, and if I'm told that I have a wire, and I also am told that I have a magnet, I have to excuse my 3D drawings here, but this is kind of behind the page, and this here is the front of the page. So here is my magnet, and there's my North Pole, there's my South Pole, and here is my current. So let's say we put a positive terminal there and a negative terminal there. Well, we can apply Fleming's left-hand rule. Now, Fleming's left-hand rule is where the thumb is pointing upwards, and that represents the motion. And it's this M here, which represents motion. And we can have my first finger pointed out, so that could be like making a toy gun in the hand, so that'd be your first finger. And that represents the field lines. Excuse me. And the second finger, as if it's a trigger to the gun, would represent the current. I'll show us a clearer picture of that in just a second. But the first letter there of first finger represents field, and second finger, so the current, second finger, both share the C there. So I can apply Fleming's left-hand rule. So if you get your fingers and thumbs out in the shape of a gun with your middle finger pulling an imaginary trigger, if you like, we can apply that to this example here. And the question would say, well, which way will the wire experience a force? Will it experience a force to the left, to the right? Will it be up or down? Will it be into the paper, or will it be out of the paper, if you imagine this as a 3D axis there? Well, I need to know two things first. I need to know the direction of the current, and current always works plus to minus, so my current is in that direction, which tells me that my second finger must be going that way. Okay, my field lines, now my field lines always go north to south, so you can feel free to draw those on your exam question. Field lines are north to south, or out of the page, as we can imagine here, out of the screen towards you. So that will be my field lines, will be my first finger. So while keeping your second finger going to the right, now point your first finger back towards yourself, and you should see that if you're keeping your hand in the right position, you should see that the thumb is now pointing downwards. So in this example here, the wire is going to feel a force which is downwards. Now, just to make sure that my drawing hasn't confused you at all, let's have a quick look here. A much better diagram of a hand. So here's my thumb upwards, fourth finger, first finger showing the field lines, and second finger showing current. So if we apply it to this example here, we can see that the field lines are going into the page, so point in towards your computer screen. We've got the current is going to the left, so my second finger goes towards the left. So now you'll have, if you like, your toy gun upside down, and your thumb should be pointing down. Okay, on this example here, we've got our field lines. So our first finger is going to be to the right, because my field lines go north to south. My current, my second finger, I can see is coming out of the computer screen, and lo and behold, my thumb is now pointing upwards. Okay, now, if that confused all of you, let's have a quick look at how we can apply it to a motor before we look at some exam questions. Okay, a typical question that you're going to be asked is, here is a motor, here's the direction of the polarity of the current, here is a magnet, what direction is this going to turn? Now, so this is an electric motor in its simplest form. A motor works because of the motor effect. Again, it's just a wire carrying current in a magnetic field experiencing a force. So this is how we can send in electricity, and we can turn electricity into motion. You may be asked which way the loop spins. It's either going to spin anti-clockwise or it will spin clockwise. The loop of wire has current going up and down it. So just choose one side of the loop. Let's either choose this side or this side to apply our Fleming's left-hand rule. If you apply it to both at the same time, you don't know where the current is coming or going, as it were. Okay, so this loop of wire through the magnet has what we call a split ring commutator. Now, a split ring commutator is simply there. If you notice, it's got a little gap at the top and a little gap at the bottom. What this allows is that as the wire flips over and over, is that the contacts change each time. So a split ring commutator allows the contacts to swap every half a turn. And all that does is it just keeps the current going in the same direction, up one branch and down the other. Okay, otherwise the motor would just flip backwards and forwards every time, and we want the motor to keep on going in one direction. So that's what the split ring commutator is. Okay, so if we want to find the direction that this motor is going to spin in, is it going to spin anti-clockwise? Is it going to spin clockwise? Well, we're going to apply Fleming's left-hand rule, as we can see down here. So pick one of the sides. Now, the first thing to do before we pick a side or try and apply Fleming's left-hand rule is, which way is the current working? Well, current always goes plus to minus. So we can see that the current here is plus. So this side is our plus side. That side is our minus side. So current will be moving up this far side and coming back this near side. Okay, so you can apply Fleming's left-hand rule to either side, but let's just start off with this far side now. So current can be thought of as going into the screen. So if current is going into the screen, that's my middle finger. So this finger here is going to be pointed into the screen. And if I look at my field lines always go north to south. So if they're not drawn on there, draw them on. And the field lines go north to south. So that's going to be my first finger is going to be pointed that way. Now that means that my thumb now has turned downwards. So this side here is going to feel a downward force. Now, if you're in any doubt at all, just apply Fleming's left-hand rule to the other side. Okay, just to make sure. So on this right-hand side of the loop, up here, we said that current is coming back this way. So our second finger is going to be coming out of the screen. Our first finger is going to be going left to right again. And this time my thumb, therefore, is pointed upwards. So if you're going to label it on the loop of wire, put an arrow on both sides to make it really clear. Or you could, at one point, just put that it is going to be moving anti-clockwise. Okay, so let's have a little look at a practice question then. So here we go. The diagram shows apparatus set up by the student, and we've got two magnets. We've got our south side here, our north side here. Closing the switch creates a force that acts on the wire XY. Well, here's my wire XY. Wire held between the magnets, and here's my battery, and here's my switch. So explain why, when the switch is closed, why it experiences a force. Well, again, stick to what to the science that you've been explained. So closing the switch makes a current go through the wire. So current in wire, for one mark, creates a magnetic field for your second mark, and this interacts with magnetic field from the magnet. In other words, I've just made a magnetic field around a wire and I've brought it close to a magnet. So of course the two magnetic fields are going to repel each other and they're going to interact. So do just make sure you include where it's interacting with the magnetic field from the magnet, from the permanent magnet. So there are your 3 marks. Okay, our next question, a few marks here. So again, highlighter out. Closing the switch creates a force that acts on wire XY again, same picture. The force causes the wire XY to move. Draw an arrow on the diagram above to show the direction in which the wire XY will move. Well, if we apply Fleming's left-hand rule, we are going to see that the current goes from so our current is going to go in this direction from plus to minus, and our field lines are going to go from north to south, and therefore my motion is going to be upright. So it is worth knowing then that on these circuits here that the long line represents the plus and the short line represents a minus. So the current is flowing plus to minus, so the current is flowing from left to right. So my second finger wants to be pointed to the right. My field lines want to go into the page, that's my first finger. and therefore my thumb is now pointed upwards. Okay, so drawing on the just how to represent that on the wire, you'd only want to put the direction of the force, which is up here. Okay, state the effect that this experiment demonstrates. Well, it's called the motor effect. The student replaced the battery with a low frequency alternating current. So that means my current is going to be flipping backwards and forwards, but at a low frequency, so reasonably slowly. The student closed the switch. Describe the movement of the wire. Well, normally we would use DC just to make the wire move once, but if it is AC, the current is going to be flipping backwards and forwards, and therefore the force is going to be flipping backwards and forwards. So we can simply say that the force changes direction. You could also say that the direction of the magnetic field of the wire changes as well. So we want to be saying that the I've got my answers around the wrong way. So the description of the movement of the wire is the wire is going to move up and down. So as the current flips backwards and forwards, the wire is going to move up and down. Or you could say the wire vibrates. Either one would be correct. And why is that? Well, it's because the force is changing direction. Okay, and we're nearly there now. So one last question is looking at the direction of side A. Side A of the coil experiences a force. Draw arrows on the diagram to or explain why side A of the coil experiences a force. Well, to explain that, the current in the coil creates a magnetic field. So this current flowing through here, you can see our direction of the current on here, so it's going to be flowing up there. Here's my arrow. So the current in the coil creates a magnetic field around the coil. So the magnetic field of the coil interacts with the permanent magnetic field of the magnets. So a magnetic field will be created around side A, and that will interact with the magnetic field lines from the magnets, producing a force. Now, drawing arrows on the diagram to show the direction of the force acting on side A. So if we apply Fleming's left-hand rule, we have current going away from us, field lines going to the right. So my second finger is pointed into the screen. My first finger is pointed to the right, meaning my thumb is now downwards. So side A is going to move down. Okay, when horizontal, side B experiences no force. Well, the reason for that is it's parallel to the magnetic field lines. So when it's parallel, it doesn't feel a force. The current has to be moving sideways or cutting through the field lines. Okay, just another couple of minutes, and we're just going to look quickly at transformers. So transformers, as well, you know, include the cables and the step up and step down transformers. So the national grid includes the step up and step down transformers and the cables. So a step up transformer increases the voltage, reducing the current, and it does this to reduce heat loss due to resistance in the cables. Secondly, the step down will reduce the voltage, increase the current to make voltage safe for homes. Now, if we look at this transformer, well, what's the science behind it? Well, a transformer transfers energy through electromagnetic induction. So what electromagnetic induction is it's the process of inducing voltage in a conductor. In this case, on the primary side, which might come from a power station, I need to stop hitting the slide there. From the power station will come current and voltage, and then connected via a iron core which is not conducting electricity. There's no electricity going through the iron core, just magnetic field. On the right-hand side, on the secondary side, is some another set of cables wrapped around this iron core. Now, there's induced in this second side is an alternating voltage and therefore current in the secondary coil. So how we work out what if I put in a certain voltage into this transformer, and I will also get a certain voltage and current out on the other side? Well, how can we work out what the voltage should be? Well, this equation over here explains it. So the voltage on the secondary side over the voltage in the primary side is the same ratio as the number of turns of this coil of wire here. So on my left-hand side on this, I have lots of coils of wire. On the right-hand side, I have fewer coils of wire. So that means that the ratio of the voltages will work in the same way. That I'll be reducing the amount of voltage because I'm reducing the number of coils here. So this here is an example of a step-down transformer because it's reducing my voltage. Now, transformers are nearly 100% efficient, so the power in also equals the power out. So we can say that because P equals I times V, current times voltage, we can say that the voltage times the current on the left-hand side is also equal to the voltage times the current on the right-hand side. So there is a changing magnetic field which is created around this primary side. The changing magnetic field happens. The same science as any wire carrying current creates a magnetic field around it. As the alternating current flips backwards and forwards, it makes the magnetic field lines change. So the magnetic field lines will be changing rapidly, and they will be felt by the cables on this side, inducing a voltage in it, creating a voltage in it. Okay, a switch mode transformer. This is a type of transformer maybe used in power stations or at the end of the road, a junction box. A switch mode transformer is one that has a much higher frequency than those used in the national grid. So a laptop transformer maybe on the box on the end of the cable of your laptop. Okay, if we have a quick look at a couple of questions. Batteries inside laptop computers are charged using laptop chargers. The laptop charger contains a traditional transformer. We can see in this question here on this side, we've got 575 turns. On this side, we've got 50 turns. So that already, I know that's going to be a step-down transformer. It's reducing the voltage. We can also see my mains voltage here, and they've also given me the current supplied to the laptop. So an alternating current flowing through the primary coil of the transformer creates an alternating current in the secondary coil. Explain how. Well, the changing current creates a changing magnetic field. So your AC current creates the changing magnetic field for 1 mark. This will cause a potential difference. So a potential difference or a voltage will be induced in secondary coil. I mean, you could say that the magnetic field will be felt by the secondary coil. That would be okay as well. And as it's felt by it, that induces a voltage across the secondary coil. And the important parts there are there to remember that it's a changing current causes a changing magnetic field, which induces voltage in the secondary coil. Okay, so 2 more questions then. Okay, so batteries inside laptops are charged using laptop chargers. The same bit of information as before. Use the diagram now to calculate the potential difference the charger supplies to the laptop. So I want to know the voltage provided on this side here. Now on this side, I know my input voltage. I know my input number of coils. and the ratio of the number of coils is the same as the ratio of the voltages. Now this equation here works either way round, so I can flip this upside down and it will still work. So if I want to know the voltage provided, that's going to be my voltage on my secondary. I divide it by my voltage by the primary, and that's going to be NS and NP. Well, because I put my voltage to the secondary up on this top here, I can simply move my voltage on the primary up here. So Vs equals NSVP over NP. So that's my number of turns on the secondary times the voltage on the primary divided by the number of turns on the primary. So that is going to be, let's give myself a bit of space here. So Vs is going to be 50 here, times by my voltage on the primary, which is 230, all over the number of turns on the primary, which is 575. Okay, giving myself a final answer of 20. Okay, one last one. So I know that my voltage on this side is 20 volts. My current on this side is 3.45 amps. So calculate the current in the primary coil. So I want to find out the current here of the transformer when the laptop is being charged. Assume the transformer is 100% efficient. Well, I can use this equation up here, that my voltage and current on my primary side equals my voltage and current on the secondary side. So IP is going to equal Vs times Is all over Vp. So IP equals voltage on the secondary, 20, times by my current on the secondary, 3.45, all over voltage on the primary, which is 230. And that should give me a final answer. There's my calculator. 20 times 3.45 divided by 230, which equals 0.3. Okay, now, ladies and gentlemen, in a nutshell, that's everything in the second half of triple physics. Sorry I've overrun just a little bit there, but I thought worth squeezing every last bit in. Feel free to rewind and speed up certain parts of this presentation as you see fit, and let me know what you think of it overall. Okay, thank you very much, ladies and gentlemen.